When we used kinematics to describe motion, there were really 5 parameters of interest that we need to completely describe the motion. The change in position or the displacement of the object, the initial and final velocities, the acceleration, and time. Kinematics, remember, is the study of motion without using forces. And we've been dealing with graphs like this velocity versus time graph. So I want to show you how we can come up with these 4 equations using this graph and what we know already about kinematics. If the acceleration is constant, we have a straight line connecting v initial and v final. The velocity is linear. And we know that our kinematics problem starts at t equals 0. That's our initial time, that's our initial condition, t equals 0. So you can see at t equals 0, I've got a dot on my vertical axis for the initial velocity. And then my final time I'm just going to call t, and at that time my velocity reaches its final velocity. I'm calling v sub f, or v final. We know that the slope of this line is the acceleration, and we know that the area under the velocity versus time curve is displacement or change in position. So using those facts, we're going to derive these 4 equations. We'll start with equation 1. This one's fairly simple because we know it's a straight line. And the equation of a line, the slope-intercept equation of a line, is y equals mx plus b. Y is our vertical axis. In this case, it's velocity. M is the slope of the line. In this case, it's acceleration. X is our horizontal axis, which is time. B is our y-intercept, and we know that that is v initial. And at time t, our velocity is v final. So I'm going to call this v final. And if I just rearrange some things here, I get v final is v initial plus at, our first equation. Let's jump to equation 4. We know that the displacement, delta x, is the area under this curve. And we're going to treat this as a trapezoid. The shape of this is a trapezoid. And so the area of our trapezoid is the base times the average height. The average height of our trapezoid is just the average velocity. The base of our trapezoid is time, t, the time it takes to get to v final, and our average velocity, because the velocity is linear, because it's linear, we can just average the endpoints to get the average velocity. V final plus v initial over 2. How do we average two numbers? We add them and divide by 2. Again, just writing it in the same form we have above. V final plus v initial over 2, which is the average velocity, times time, gives us the displacement. There's equation 4. Now let's take a look at equation 3. Again, we're going to use the fact that the area under this curve is our displacement, delta x. But this time we'll split our curve into 2 shapes, a triangle and a rectangle. Area triangle, area rectangle. We know that the area of that triangle is 1/2 times the base, which is t, times the height. And what is the height? It's v final minus v initial. This height right here. We know that the area of the rectangle is the base times the height. and we're going to add these up. There's the area of my rectangle. The area of my triangle, I'm going to write it a little differently. Instead of v final minus v initial, I'm going to use a result we got earlier. For equation 1, we got v final is v initial plus at. That means if I move v initial to the other side, v final minus v initial is just at. So instead of v final minus v initial, I'm going to substitute in at. And that is equation 3. The last one, we're actually not using our graph. We're using two of our previous equations, and we're just going to eliminate t. If you notice, equation 2 is the only one that's missing time. So we can take two of the other equations, eliminate t, and we'll get this equation. So we've solved for t using equation 1. We're going to plug that in for t into equation 4. And we'll eliminate t and get our change in position is our average velocity times time, but instead of t, we're going to put in v final minus v initial over a. We'll multiply through by 2a. We'll multiply through these parentheses to get rid of them, and we get v final squared minus v initial squared on the right side of the equation. And we can rearrange this to give us which is what we had earlier. That's how we derive these kinematics equations, simply using the graph. In the next video, you'll see how we can derive them using calculus.